Hi students, today we are going to cover the magnetism. In ancient times, Greece people found a rock that attracts iron, nickel and cobalt, and they called them as magnet. And magnetism comes from here. These rocks are used later by Chinese people to make compasses. So the needle in a compass is also a magnet. Magnetism exists always in dipoles. North, which is represented by N, and the South Pole, which is represented by S. If you break the rock into pieces, then you get small magnets with again two poles, north and south. So you can't divide the poles of a magnet. Same poles of the magnet, like in the electricity, repel each other and the opposite poles attract each other. Here you see that north and south poles attract each other, while the same poles, south and south, north and north, repel each other. The strength of these forces depend on the distance between them. The closer they are, the more force they apply, and the intensity of the poles. Let's do an example. We have three magnets. When the system is released, the magnet B gets closer to magnet A. Find the possibilities of pole types of 1 and 4. As B is getting closer to A, that means that there is an attraction force between A and B and repulsion force between B and C. As A attracts B, then if the 1 is north, then 2 should be south. So 3 should be north. As 3 repels 4, this should also be north. If 1 is south, then 2 must be north because attract each other. Then this is south. As 3 repels 4, then this should be south. The magnets show repulsion and attraction force around itself. This area affected from the force of magnets are called magnetic fields. The shapes of magnetic field lines shown in the picture given below. The magnetic field is directed from the north to south pole, outer region of the magnet, and inside the magnet it is from south to north pole. So when we have the magnetic field lines between unlike poles, you see that the magnetic field lines are directed from north to south. If we have the magnetic field lines between the like poles, you see that it's getting from north poles and there is no intersection between the magnetic fields. The properties of magnetic field lines. Magnetic field lines are defined to have the direction in which a small compass points when placed on a location in the field. You see here that it is directed from north to south. When you put a compass on a magnetic field, the direction of the compass will be in the direction of the magnetic field from south to north. The strength of the field is proportional to the closeness or the density of the lines. The closer the lines, the strength is bigger. As the density of the lines gets less, then the intensity decreases. If the interior of the magnet could be probed, the lines would be formed to form continuous closed loops. You see that the loops are closed. There is no beginning and an end. They never intersect. If they're parallel, we say that there's a regular magnetic field and they are vector quantities. The unit of magnetic field is Tesla or Gauss. It is measured by Tesla meter, and 1 Tesla is equal to 10 to the power 4 Gauss. Now let's examine the properties of magnetic property of materials. We have the term magnetic permeability. That's the quantity of ability to conduct magnetic flux. Magnetic permittivity is a distinguishing property of matter. That means that every matter has a specific magnetic permeability. We group them in three categories. The magnetic materials, they weaken the magnetic field inside. They are slightly repelled to a magnet. You see here that first I have a regular magnetic field, let's say in a vacuum. When I put a diamagnetic material inside a regular magnetic field, you see that the lines are getting away from each other, so it weakens the magnetic field of the medium. The examples are diamond, gold, and silver. And we say that the relative permeability, the mu of this matter, is a little bit lower than 1. The second one is paramagnetic materials. They strengthen a little bit the magnetic field inside. They are slightly attracted to a magnet. Their magnetic permeability is a little bit bigger than 1. The examples are aluminum, tungsten, lithium, magnesium, sodium, and platinum. It is a little bit like the ferromagnetic material, but not strengthening so much as ferromagnetic materials. The third one, ferromagnetic metals, they strengthen the magnetic field inside. Their relative permeability constant is higher than 1. For example, iron, nickel, and cobalt. When you put a ferromagnetic material inside a magnetic field, you see that the lines are getting closer to each other, so the strength of the magnetic field increases. Now in this example, we have two magnets. What would the resultant magnetic field look like? Here I'm going to look for that the magnetic field lines are directed from north to south. So I'm going to look for this direction. In A, the direction of magnetic field is getting inside north, so it is wrong. In B, the magnetic field is directed from north, it is okay, and it is inside the north, getting from north to south, so B is true. Let's do and see. It is getting inside to north, so it is wrong. Getting from north, it is true, but also directed from south, it is false. So B is the correct answer. We have given identical magnets. They are in equilibrium. The tension in the ropes are T. I'm going to find the poles K, L, and M. There's no friction and X is not moving. As there is a tension in the rope, that means that X is attracting this magnet. So there's an attraction force between these two. Again, there's a tension, so this magnet is also attracted by X. So I'm going to look for attraction force possibilities. If K is north, it attracts south. So this is also north. North attracts south. If K is south, so it will attract north. So this will be south, and south will attract north. So there are two possibilities.